the convincing argument. Right? One by one. Yeah. All right. And see if you agree or not. The first one. Yeah. Imagine that mean is the final winner. So at the end, after we compare all those elements, the function returns the value stored in this mean, then that's the final winner. So it's correct. Okay? Yeah. The solution, our current solution is correct. So we have no problem on that. But the question is if it's optimal or not. We want to show here, convince people, it is optimal. It is optimal. So nobody can use fewer than n-1 comparisons to solve this problem. That's our goal. We want to convince people. Next argument, statement. It needs to beat, so this winner element needs to beat all the other elements in the array through comparisons, directly or indirectly, because we allow indirect comparison, directly or indirectly. By transitivity, it's okay to beat. Okay? Yeah. So this is the second one. Yeah. Next one. If an element loses once, it is eliminated. If an element loses once, it cannot be the winner, right? It cannot be the final winner. If it loses once, if it cannot be the final winner, can we eliminate it from the consideration? No. No, because we only want to get the final winner. Okay? Yeah, so this is also correct. All right. Each comparison can only eliminate one element, right? Each comparison, because each comparison you get one winner, one loser. You can only eliminate the loser, right? Can you eliminate the winner? No, that's not right, right? The winner eliminated from one comparison. That's ridiculous, right? So one comparison can eliminate at the most one element. Here I put at the most one. Why? Because you may do redundant comparison, right? Think about it. If you do redundant comparison, you do not eliminate any new element, right? Because you do something unnecessary. That's possible. Because some bad algorithm may do some redundant comparison. You don't need that comparison. But people just do redundant. Okay? Yeah. So here we can make this statement. One comparison can only eliminate at most one element. If it's redundant, you eliminate zero new element, right? Yeah. But if it's a good one, if it's a non-redundant one, you can only eliminate one element. That's this statement. Next one. Yeah. Yeah, here, at most one. Yeah. Factor in the redundancy consideration. Then the last one. Because in order to get the final winner, this final winner needs to eliminate n-1 elements, right? This final winner needs to eliminate n-1 elements directly or indirectly. Could be indirectly. Yeah? Indirectly. Okay? Eliminate. Right? Yeah. So then, because each comparison can only contribute at most one elimination, right? Each comparison cannot contribute more than one elimination, right? But here, we need a total n-1 elimination. So we need at least n-1 comparisons, right? Yeah. Because one comparison, you can contribute at the most one. You may need more comparisons than the number of eliminations, right? Yeah. But at least you need at least n minus 1 comparisons. So after this statement, our conclusion, so we need at least we need at least n minus 1 comparisons to eliminate n minus 1 elements. That means you cannot do better than n minus 1 comparisons. That means you cannot use n minus 2 comparisons to solve the same problem. You cannot use n minus 2 comparisons to solve the same problem, because it is already optimal. This n minus 1 solution is already optimal. Okay, nobody can do better. Nobody can do better. This statement covers all the unknown algorithms that solve this problem. Even unknown. Yeah, because we use the common property, right? This elimination, all these statements, they're talking about common properties, right? Common properties for all such algorithms. So even unknown algorithms, these properties must be true, right? Yeah. So we get our conclusion. Okay? Yeah. All right. Now you can answer question 10 of quiz 1. After this slide, you can answer question 10 of quiz 1. Okay? Yeah. All right. Yeah. So we finish this topic. Yeah. Finding the minimum, this topic. All right. Next, D.2, application. Finding maximum and minimum. Yeah. Here, we want to apply the solution from D.1. Yeah, we learned something. So the idea, the main idea in our solution of D.1, actually the optimal discussion. D.1, that's the elimination method. Yeah. Elimination method. So for this class, that elimination method is very important. Here I want to apply the elimination idea to solve another problem, another related problem. Here we know finding maximum, finding minimum, almost the same. Yeah. Just the two different cases. Yeah. But the question here is, this application, the question, finding both maximum and minimum in the same algorithm, not separately, okay? Not separate. First you find the minimum, second you find the maximum. Yeah. Your goal, you want to find both maximum and minimum in the same array with the minimum number of comparisons. That's the question. Okay? Find both maximum and minimum in the same array with the minimum number of comparisons. That's the we are given an array with n distinct elements. In order to simplify the situation, so we consider the elements are all distinct. Our goal, how to find both maximum and minimum simultaneously. Yeah, simultaneously. Yeah. Yeah. So when you see that, because many students ask me, what do you mean simultaneously? Yeah. All right. So here, in our solution, you need to produce both maximum and minimum. Okay? Yeah. In one run. Okay. So when you run your program, you need to produce the output, both maximum and minimum simultaneously. It's not like the first time you produce maximum, second time you produce minimum. It's not like that. So one run, your program must produce both maximum and minimum. Okay? So that's the requirement. All right, so now, so let's try to solve this problem. Yeah. First try, if I ask you to solve the first try, you may apply our previous solution directly, right? So I believe most of you just apply our finding minimum solution. We already have that. Do you want to apply that solution directly? The first try. Okay? All right. Let's try that. The first try, because the first try may not be the best solution, but we can get some experience. Yeah. All right. So in our first try, let us apply our previous solution to find the maximum. How many comparisons do we need to find the maximum? N minus 1. Okay? All right. All right. So here, the step 1, we need to use N minus 1 comparisons. But that's for the max. Okay? Not done yet. You need to find minimum next. How many more comparisons do you need to produce the minimum next? Second round. First round, maximum N minus 1 comparison. Second round, you need to produce the minimum.
N minus 2.
Good, N minus 2. Yeah, because the maximum can be eliminated, right? Distinct elements, the maximum cannot be the minimum, right? Distinct, okay? So you can eliminate the maximum from the consideration. So you only have N minus 1 elements. Find a minimum in N minus 1, you need N minus 2. 1 fewer. The total number of elements minus 1. 1 fewer than the number. So the second round, you need N minus 2 comparisons. For minimum. What's the total? Okay? Correct. Total 2n minus 3. Yeah. That's the direct application of our previous solution. Yeah. Now, the next question. Yeah. Remember, every time after we find a solution, we need to think about, is this algorithm can be further improved? Post-thinking, post-solution thinking, okay? Can we further improve this algorithm? Yeah. So, do you have any idea improve?
Yeah, with the elimination thing we were talking about before, to find the, so like if you use that to find the maximum, then to find the minimum, you only need to compare the ones that were eliminated in the first round. Because all the other ones.
Yeah. Sort of. Yeah, good. Yeah, I understand your point. Yeah. So what you said, yeah. But implementation could be hard, but the point is useful. The point is, in our first round comparisons, we may get useful information. We don't want to throw away. Can we keep some useful information in the first round so we can repeatedly use the useful information in our second round? Yeah, but it's hard, right? Yeah. How do you keep track of the comparison result in the first round? That's not easy, right? Yeah, that's not easy. Yeah. All right. So we need a smart way to help us keep track of some related comparisons. Now, if we can solve that problem, we can do better. We can do better. Okay? All right. So here, there is a main step we need to consider here. So here, related to our first question in our first lecture, that chessboard, I make that important point. It is important to organize the data, right? That's important to organize it. Here, in this array, how do we organize our data in this array in a convenient way for this problem? That's important. How do we organize the data in this array to make it convenient for our new solution. That's the main step we need to consider. The key to the success here. Okay, all right, yeah. So let's continue. Yeah. So let me, where is, oh yeah, here. All right. All right. Our data here, okay, yeah, in this array. So now, review elimination method. Yeah. We want to use elimination method. Okay. Yeah. So the general understanding of the elimination method, when certain elements do not satisfy the criteria, all the requirements, yeah, all right, we can eliminate them from the consideration. Yeah. So here, maximum, minimum, we have some requirements here. Okay. Since the data size is reduced, we can achieve better efficiency. Oh, yeah. Yeah, because, yeah. So this is another observation. Another observation, yeah. When we process array with smaller, because after elimination, the data size becomes smaller, right? After elimination, you only need to work on fewer number of elements. Then you can do better. Yeah, we can do better. So that's the main point of the elimination method. Yeah. But here, in order to facilitate discussion, I use some simple notation here. Okay, when we do comparison, I write pair of parentheses covering a pair, xi, xj pair. Yeah. So this pair, parenthesis, means it is a comparison, and xi is the winner. Yeah, I use this arrow. So after this comparison, the winner is xi. I introduce this notation here. Okay? Yeah. The winner is xi. Yeah. All right. The winner is determined based on the requirement. The maximum, minimum, which one is the winner. But here, we need to do both maximum and a minimum. Let's just use the winner means the greater one is the winner. That's easier. Because that matches our intuition, right? Otherwise, we need to make opposite of our intuition, right? Here, the greater one means the winner. Yeah. So matching our intuition directly. Yeah. All right. Now, details of the data manipulation. Now we can work on the data. Work on the data. Let's organize our data in a convenient way. Yeah, it's important. Organize our data in a convenient way. How to organize our data? So we organize our data for comparisons, grouping the data in pairs. Grouping the data in pairs. The first two elements, let's make one pair. Next two elements, another pair, and so on, until we pair all the possible elements. Yeah. So in a sports game, you can imagine we apply the tournament method. Okay? Every two players, they play one game, okay, between them. Yeah. Yeah. So we paired all the possible players in one tournament, the first round. Okay, the first round. Yeah. All right. But there is a special case. Can we get all the elements paired? We need to consider even odd case, right? Yeah. For odd number of elements, then one element left without pairing. One element left. For even case, then you can pair all the elements. Yeah. So we have two possible cases. when we have two possible cases, which one should we work first? Two, even or odd, which one you want to work first?
Well, do we have any prior knowledge, or would we just be guessing?
Prior knowledge.
Not the hottest.
Well, if we do an even number of elements, then we know that they can all be
Right. So, all right. So here, the prior information, just the number of elements, even or odd. There are two cases. Yeah. When we work, remember last time the strategy I mentioned, when we have multiple cases, we want to work on the easiest case first. Even case, okay, which one easier? Even. Because all elements are paired. That's easier, right? Other case, there is one singleton left. You need to treat it differently, right? So let's delay it, okay? The other case, let's delay it. Let's work on the even case first. That's what I mean, okay? All right. So the number of elements could be even or odd. When we have a few cases to consider, we always work on the simplest case first. Yeah. Because when we work on simpler case first, the solution is easier, and we can also get experience from finding the solution. Yeah, we can get experience. Okay? Yeah. All right. So let's do the work. Yeah. So this slide, I want to show you the detailed work up, and we at the same time I want to show you how to apply the elimination method on this question. Yeah. All right. Now we consider even case. So here, let's assume n equals 2k, even case. Yeah. So when we do the pairing, yeah, can we do this way? So here, x1, x2, the first pair. Okay, I use this vertical way to arrange the elements in order to get a convenient visual display. Okay, all right. x3, x4, x5, x6, dot, dot, dot. The last one, x 2k minus 1, x 2k. Total k pairs. Each pair, we do one comparison. One comparison. One greater than the other. We assume distinct. Okay? So we do not consider the equal case. One must be greater than the other. Yeah. All right. Here. Because for each one, two possibilities. Yeah. x1 greater than x2 or x1 less than x2. Each comparison, two possible results, right? Yeah. Two possible outcomes. Yeah. In our discussion, if we consider all the possible results, is it too messy? Very messy, right? Yeah. So, in order to make our discussion as easy as possible, can we make assumptions? Can we make assumption the top one always beat the bottom one? Can we make that? If not, if the top one's smaller, can we flip? Yeah, because you flip. I mean, we just, after each comparison, we just make the top one greater one, bottom one less one. Yeah. The subscripts not that important, right? Yeah. The subscripts, if we want to change, we can change. Okay? Yeah. So for our, discussion, make our discussion as easy as possible, we assume the top line, the winners group. How about that? The winners group, top line, the bottom line, the losers group. How about that? Okay? That's our assumption. Yeah. Our assumption. Yeah. So you see, this one, the winners group, this one, the losers group. Right? The first round comparison, how many total comparisons you need to get winners group, losers group? How many comparisons do you need?
N divided by 2.
Yeah, n divided by 2. Yeah, correct. N divided by 2. That's k comparisons, right? Yeah, n equals 2k. Okay. Yeah. So this round, the first round, we need a k comparisons. All right? Yeah. Then we move to the second round. All right. Next round, we need to find both maximum and minimum. Okay? In order to find the maximum, where should we look at? In order to find the maximum element, where should we look at? Yes. Yes. Winners group, right? Not in losers group, right? Not in losers group. So we can safely eliminate maximum from the losers group. Elimination method. Yeah? So we only need to consider the winners group, or maximum in the winners group. How to find the maximum in the winners group? How many comparisons do you need? K over 2. How many total elements in the winners group? K. So how many comparisons to find the maximum in the winners group?
Are we using the same method where we divide them into subsets again?
Yeah, same method in the previous solution. Minimum, maximum,
Oh,
D.1,
K minus 1.
K minus 1. Okay? So the second round, we need K minus 1 comparisons in the winners group to get max. Similarly, K minus 1 comparisons in the losers group to get minimum. What's the total number of comparisons? K plus K minus 1 plus K minus 1 equals 3K minus 2. K equals N over 2, right? 3N over 2 minus 2. The answer. Okay? In this way, you can see the answer, if you compare with our first try 2N minus 3. This one better, right? Can you see? Because this one, the coefficient of n is 3/2. Coefficient of n is 2. 3/2 less than 2, right? 1/2 better. 1/2 n better. That's a lot. That's a lot. Okay? Yeah. Yeah. All right. So then, after we find a solution for this even case solution, is it optimal? This one. Is it optimal? Yeah. Yeah. It's hard to see if it's optimal or not, right? Yeah. Yeah. So here I can tell you the result. It's optimal. To show it's optimal, it's very hard. I can give a reference. Yeah.
Would it
To show it's
not be
No. Yeah. So you do recursion. Yeah. Yeah. Now, because you only need to find the maximum. So you don't do the recursion. Yeah. Because in winner's group, this is optimal. This is the best you can do already. So you don't try to beat this one. Okay. Don't try to beat this one. Yeah. Because we already know they're optimal. Right? Yeah. Yeah. So, all right. But so here I only tell you the result. This algorithm is optimal to solving this both maximum minimum simultaneous. It's optimal. Okay? Yeah. So there is a argument. Yeah, but this argument, much harder than the previous one. Yeah. Yeah. So I can, yeah. So if it's possible, I can find that argument, for your, for your interest. If you want to study, yeah, I can show you somewhere. Yeah. All right. So that's first one. Yeah. Yeah. Second one, another question. If we consider n is odd number, n equals 2k plus 1, can you see how do we modify this solution to get n? Oh, sorry. Yeah, too sensitive. Yeah. All right. Yeah. So if n, yeah, something is wrong. Yeah. Suddenly, yeah. All right. Yeah, this looks well, all right. If n equals 2k plus 1, yeah. The second case, yeah. Here, where's that? Here, all right, 2k plus 1, yeah. Because it's closely related to the even case. The question, how do we modify? So we don't want to start from scratch, right? How do we just modify the even case slightly so that we can solve the odd case?
Yeah. You could take that odd one and save it till the very end and then compare the winner of the winner's group and the winner of the loser's group.
Good. Yeah, that's the modification. Yeah, exactly. Like, so we have a singleton. Yeah, the last one. Yeah. The last one, because we do not do any comparison, last one, the singleton one, okay? But when we consider the winner's group, we should include the last one, right? Yeah. Because it could be the winner, right? It could be the maximum. So we should, in the winner's group, we should include the last element. In the loser's group, we should also include the last element, right? Because it could be the minimum, right? Yeah. So then we just modify slightly. The first round, we still do these k comparisons. The last element, we assign it to both groups. Yeah, both groups. Then our second round, the number of elements minus 1 for the maximum, the number of elements, the minimum, yeah, and total. Okay? Yeah. So I just give you this idea. Yeah. So you should be able to complete it. Okay? So if I give a specific number, yeah, here I use the n, even, odd, but in my exercise questions, I may give you concrete number, like 101, n equals 101. I ask you how many comparisons you need to find both maximum and the minimum. Okay? Yeah. All right. So that's this question. So we finish this topic. All right, selection sort. All right. So let's solve the problem. Problem number 4, sort an array. Given an array, how to sort it in ascending order. Yeah. The problem, very short. Yeah. Let's find our first sort solution here. Yeah. All right. The problem type sort. Yeah. All right. Let's do analysis. Yeah. Look at the title. So here I want to convey this point. We want to find a solution from our experience. Yeah. At this point, our experience, module 1 is our experience. So we want to use our experience from module 1. Yeah. All right. So let's explore the properties. Yeah. All right. Yeah. Here, we use the backward thinking. Yeah. So it's very common in problem solving. Yeah. Assume the problem has been solved. Assume we have sorted the given array in ascending order already. Yeah. Okay? Yeah. So let's look at what property can we discover in a sorted array. We already sorted. Can you discover some special property so that we can take advantage? We can apply this property to sort a given array. Yeah, that's the idea. Yeah. Yeah. Here we assume distinct elements for convenience, yeah, for discussion. Later, if the element's not distinct, we just modify our algorithm slightly. Yeah, so we can get it. Yeah. All right. Now, our experience. The experience for module 1. What experience we should use? How to connect this problem to the minimum problem. Yeah. Minimum problem is our experience. We know how to find the minimum, right? We know how to find the minimum. So here the question. Can we connect this sorting problem to finding the minimum problem so that we can apply the solution in the minimum problem to solve the current problem? That's the direction to go here. Okay? All right. Observation here. Here, assume the array has been sorted in ascending order like this. Okay? Yeah. Now, if you look at this result, sorted array, ascending order, can you see something special here? Related to the minimum problem? Some property is special related to the minimum problem? Which element is the minimum? First one. First one. Okay? Yeah. So here, can we understand in this way? If we can find the minimum of the whole array, we know that minimum should be the first element in the sorted array. Yeah? That minimum, you know the first element in the result array. Okay? That's the key observation here. That's the key observation here. Okay? All right. Yeah, so here, A0 must be the minimum of the whole array. Yeah. Yeah. So here, I use the subscript 0. Yeah. The first round, we find the minimum. Yeah. First one, we find the minimum. So we get that minimum. That minimum should be the first element in the destination array. Yeah. All right. After we get first element in the destination array, can we eliminate it from the consideration? Because it's already in the destination. We do not need to touch it anymore, right? Yeah. Already in the right place. That element is already at the right place. We call it, we use a terminology here, we call it in place. So this element is in place. It's placed in place. Placed in place, that means that's at the right place in the final destination array. So we should not touch it anymore, right? Yeah, yeah. It's perfect. For the first one, right there. Cover it. Yeah. Cover it. Then let's look at the remaining elements in the array. Yeah. Remaining elements. Then A1 should be the minimum of the remaining elements, right? Can we apply the minimum problem solution another time to get A1 and so on? So that's the solution called a selection sort. Why selection sort? Because the minimum problem we call a selection problem, right? So every time we solve a selection problem, we get a one element in place. First element in place, second element in place, third element in place. At the end, we put all elements in place. Then we get the whole array sorted. That's the idea. That's simple. Okay? Yeah. So here, you see, that's the way solving the problem from our old experience. Selection problem.
What about doing the minimum and maximum at the same time?
Oh, good idea.
Reduce the array by 2.
Yeah. Good. Yeah. Yeah. Minimum, maximum at the same time. So we put two elements in place. Good. Yeah. Then we can improve, right? We can do better than this one. Yeah. That idea. Yeah. Definitely, if you do it that way, you can do better. You can do better. Yes. Good point. Yeah. So I may create an exercise question using this idea. Okay? Exercise question. Yeah. Good. Yeah. All right. Yeah. In place concept. The element is placed at the position when the array is sorted. Yeah. So we call it in place. Yeah. All right. Then we just use the elimination method. Yeah. All right. Yeah. So that's this solution we call a selection sort. Yeah. All right. Then we want to how to make all elements in place. Yeah. So here I use this diagram. Yeah. Just the first time we put the first element, the minimum of the whole array, the first element in place. The second time, so then we eliminate the first element from the consideration. Yeah. Then the remaining elements, we find the minimum, the second element in place, another in place, and so on. At the end, we put the last element in place, all elements in place. So we get it sorted in this diagram. Yeah. So the conclusion, when all the elements in an array are in place, this array is sorted. Yeah. All in place. All right. Efficiency analysis. Now, after we get the solution, we want to know the number of comparisons. We need to count how many comparisons do we need to get this solution. Yeah. All right. Count the number of comparisons. Yeah. When we put the first element in place, we need this many, right? N minus 1. Find the minimum. Yeah. The second one, the second minimum, we need N minus 2. The third minimum, N minus 3, and so on. Okay? Yeah. And second to last one, we need one comparison. The last one, we don't need a comparison, right? The last one, because the only one left, there is only vacant location left. So this element can only go to the last available location. No comparison needed. Yeah. So the total number of comparison, if we come from the, one here, 1, 2, 3, N minus 1. So we add up these consecutive integers, and we get this many comparisons. Yeah. All right. Yeah. Total number of comparisons. using the selection sort. Later, we will look at other sorting algorithms. This is our first sorting algorithm. We will learn several more sorting algorithms here. All right, now the question. If we use the selection sort here, what is the best case? Remember, we talked about the concept. Best case, worst case, and average case when we learn the linear search, right? Linear search.
Best case would be that they're already sorted.
Whatever, yeah, so the given input, given array, you can assume already sorted. If the given array is already sorted, how many comparisons do you need? If the given array already sorted, n minus 1. All right, so, yeah, given array already sorted. Yeah, how many comparisons do you need to find the minimum? Oh, the first minimum.
Well, if you know it's already sorted, then you just need the first one.
Just one.
Yeah, if you already know it's sorted.
Okay, all right, yeah. All right, so here, there is an important concept. Yeah, so first, all right, here, let me just, shut down this one. This one, because I don't need this one. All right, let me just, let me explain this last point before we leave today. All right. You can consider the input array is already sorted, but you don't know it. How about that? The input array is sorted. We know, because when we write our program, we write implementation instructions, right? When we write the instructions, usually we do not check if the array is sorted or not, right? Yeah. And if the data happens to be sorted, you don't know it, right? In your program, because you do not check the array is sorted or not, people do not check the data because you need to use many comparisons to do the checking. It may not worth it. Yeah, because too much work. People never do the checking because that work, in general, you cannot get the payback. That amount of work usually wasted. Okay, so people never do it. Do the checking. So if you do not do the checking, if the given array is sorted, you don't know it. How do you know? You can use, it's sorted, right? You don't know it's sorted.
No,
it's happened to be
sorted after you sort it again. Like,
right.
If it's
Here.
been already sorted, you still
Right.
have to
Yeah.
sort it.
Yeah, you still have sorted. You cannot skip any step here. You still need to find the first minimum, second minimum, third minimum, and so on. You still need to do all the work. Okay? So the result is same number of comparisons. Even if it's sorted, you still need this many comparisons. You cannot save any. Here, what I mean for this particular problem, okay? Yeah, for this particular problem, because later we have a different sorting algorithm, that sorting algorithm could take advantage of the order information. Yeah, there is another sorting algorithm. You do not need to do the checking. The sorting algorithm automatically takes advantage of the order information. Yeah, later we will be there. Yeah, but this one, it does not take advantage of any order information. So you still need to do this many comparisons for best case, for worst case, for average case. For any case, you need this many comparisons. For any case, no difference. No difference. Or you can understand this way, there is only one case. For this selection sort, whatever input is given, you only have this one case. One case. So best case is this one, worst case is this one, average case also this one. All the cases. This one covers all the cases. Okay? All right, so here we finish selection sort, the first topic of Module 2. All right, so let's stop right here. So next time we will do the remaining